on the positions of these binding energies. We've improved already by almost an order of magnitude the known binding energies of some of these weakly bound levels, so that now they're known to just a few kilohertz. And this completely systematics limited. At this point, we can do better because we have good statistics. And actually, this was a new thing that we didn't know, that there was this degeneracy of almost a near degeneracy of two extremely weakly bound levels right near their shelf. This high precision is important, as I'll show you in the next few slides. So one interesting effect that we discovered is that if you look at these very weakly bound molecules near the singlet triplet threshold, we get anomalously large Zeeman shifts. So again, this is this trace of strontium-2 molecules, this atom recovery or molecule fragmentation trace, and so we zoom in on these two peaks. So this one here, and this one down here, and these are taken under a weak applied magnetic field, just on the order of a Gauss here, about 3 Gauss here, less than 1. And even at these very weak fields, you can see extreme asymmetry in the splitting, in the Zeeman splitting. So when we plot the peak positions versus the field, we get extremely curved lines, which means that the quadratic Zeeman shifts are extremely large, which we didn't quite expect, because here, just the comparison again of this molecular, very curved Zeeman shift with the atomic ones. So remember, this molecule is extremely weakly bound. There are almost two free atoms. One is singlet S, the other triplet P. So we can look at the atomic Zeeman shifts on that transition. And then, of course, so the G factor for the atomic transition is 1.5, and we get basically straight lines for the linear Zeeman shift. There is some quadratic component that you can characterize as quadratic coefficient by chi, and it's about 0.4 hertz per Gauss squared, so it's tiny as expected. However, when you look at the bound atoms, even extremely weakly bound, this this quadratic Zeeman coefficient is 0.4 megahertz per Gauss squared, so it's enhanced by a factor of 10 to the 6, even though they're so weakly bound. So that was quite puzzling. Of course, another puzzling thing was that even the linear shifts were unexpected. In fact, for this particular level, that corresponds to the omega of 0 in the excited state, or the potential. Remember, the excited state had two potentials, so this one corresponds to the one that's supposed to have no linear Zeeman shift, and yet these levels had large Zeeman shifts with effective Gs of 0.1 to 0.9. So both the linear shifts and the quadratic shifts were huge compared to what we thought they should be. And so we can plot this effective quadratic coefficient for various levels near the asymptote. We can plot them versus the binding energy. So this is the log plot of binding energy. So this is going toward the continuum. This is the weaker binding energies, and this is the enhancement factor compared to the atomic case. So you can see it really gets up to more than 10 to the 6 when we get really close to the asymptote. For this magnetic susceptibility is that chi, the quadratic magnetic shift coefficient. So these are plotted for various quantum numbers, but we also have a simple model that's supposed to kind of give you some intuition and predict and explain these large shifts. And that simple model is plotted here as a gray line. The model is only applicable to some of these black square points, and it actually agrees very well with them. So even though our colleagues have a very fancy ab initio model that actually gives out these coefficients very, very, very accurately, I think it's nice to understand also intuitively with a simpler model what happens. So we explain this anomalous quadratic Zeeman effect by strong non-adiabatic mixing of the two potentials. So non-adiabatic usually refers to some mixing of electron dynamics with nuclear or rho vibrational dynamics. So this mixing is called non-adiabatic physics. And here, it's actually, it's very important that we have these two potentials, because right near the asymptote, they get extremely near each other. And so weird things happen. So you can, first of all, these potentials are dominated by the C3 term. So in the long range, one goes roughly as C3 over R cubed. The other is minus 2 C3 over R cubed with the same C3. Now, you can, again, this is the definition of chi, is just basically the quadratic Zeeman shift coefficient. And this chi can be roughly estimated sort of by, if you think of perturbation theory, where the difference between the two potential energies goes in the denominator. And then the difference between these two is exactly 3 C3 over R cubed. So because it's in the denominator, R cubed goes to the top. So what you end up having is the magnetic susceptibility that is proportional effectively to this volume of the molecule, or the length cubed of the molecule. And with a very narrow line width, like we have in strontium-2, one can resolve molecules that are so close to the continuum that effectively R is huge, it's 500 Bohr. So we see this cubic scaling all the way to very enormous Zeeman shifts. So sort of intuitively, we understand it also quantitatively as well. Now, so that's the interesting part about the quadratic Zeeman shift. Now we can think about the linear Zeeman shifts. What do they tell us? Or essentially, what can we learn from these molecular G factors that we measure? Again, so we have those two potentials, one that's labeled with a 0, one labeled with a 1, that come together near the asymptote. And without any mixing, without this non-adiabatic mixing, the levels belonging to each of them would have just fixed G factors. In fact, one would be 0 and one would be 3/4. But that's completely not what we see. Therefore, we conclude that there is strong non-adiabatic, or also so-called Coriolis mixing between them. We can parameterize this mixing between the two potentials by some angle theta, this Coriolis mixing angle. So we can write each vibrational and rotational level near the asymptote as sort of the sum sine theta of the level with a 0 omega and cosine theta times the state with omega of 1. Just taking the expectation value of the linear Zeeman Hamiltonian, in this case, one can write down the expression for the expected G factor, so divided by the atomic G factor, which is 1.5. And this ends up being a function of the mixing angle theta, of course, because the quantum state is a function of theta. So here I plot this molecular G factor as a function of theta for a particular choice of J prime of 1. So you can see this function, and it really covers a huge range of G's. So you can, depending on your mixing, you can measure almost any linear Zeeman shift between -1 and 1.5. So here I marked a few of the levels that we have actually measured, and you can see. So one problem with this is that this function is double valued. So let's say you measure a G factor, it could still correspond to 2 possibilities. So that's something that experimentally is difficult to resolve, but we do have access to a very good ab initio model, and so some of these. So let's say the experiment will give you something like 16 degrees and 95 degrees, and it'll be really obvious from the model which one is correct. So with just with a slight help from the model, we can resolve which one of the two values is correct for the theta. It turns out that there are a couple of levels that are extremely strongly mixed that you can see with these light gray arrows, where it's just not, we just can't tell which one is correct. We can only tell that they're very strongly mixed, and it's one of these two angles. But for most of the cases, we can really very precisely maybe to less than 0.1 degree figure out this angle just from the size of the linear Zeeman shift. So this is kind of interesting because this mixing is kind of a subtle parameter in the molecular wave function, and I think it's kind of interesting to have a direct access to it spectroscopically. Okay, so these magnetic shifts are one of the weird things that occur near the asymptote. Another weird thing that we like to look at is potentially different types of forbidden transitions that might be not so forbidden once you get into this weakly bound regime of a very large molecule. And there are two types of forbidden transitions that we look at. So here, I call it the field-assisted doubly forbidden transition. So why doubly forbidden? So all of this is a singlet to triplet, right? So these are all forbidden transitions. That's why they're so narrow. But doubly forbidden, in this case, means that a delta J change of total angular momentum is 2. So for electric dipole transition, that's forbidden. But since we have very funky Zeeman shifts, we might think that, well, even with small magnetic fields, one might be able to mix the levels a lot and so see something like this. So here I plot, again, Zeeman shifts in megahertz versus the applied field for a different kind of level that I didn't show before. This is an even angular momentum level. So that's in itself kind of interesting because it's been mentioned before that one might not be able to see them because they have different what's called spectroscopic parity. But anyway, it turns out we can see them and we can measure their Zeeman shifts. The Zeeman shifts are very weird because for these plus minus 1 components, it's very strong, not only linear and quadratic, but also cubic and quartic. So you can have very asymmetric Zeeman shifts for these levels. It's kind of very strange. But the fact that the Zeeman shifts are so extremely strong does hint that maybe we can use very small fields to mix them up and see these forbidden transitions. So just one example of a transition that we think we can definitely induce with application of small fields is a particular one with delta J equal 2 to this even J angular momentum, so to even J level that's bound by about 300 megahertz. And you can see the transition strength. We sort of had to carefully figure out how to quantify transition strength, but I think this is a pretty good measure versus magnetic field. So near 0 is basically forbidden as expected, but just a few Gauss to a few tens of Gauss make the transition stronger by about 5 orders of magnitude. So it's kind of very unusual. I don't know if this particular one is useful, but certainly people do use field-enabled forbidden transitions, for example, in the field of atomic clocks, where sometimes they apply a very tiny field to be able to drive a transition that's intrinsically forbidden, but with a field that's slightly allowed. So certainly in metrology, this can be useful. Moreover, there's another type of forbidden transition with a very different property. So we expect that near the asymptote, we can see unusually strong magnetic dipole transition. So everything I talked about before was electric dipole, just simple what we were used to. Now, there is a kind of transition that's forbidden electric dipole-wise. And this has to do with the molecular symmetry. So for a diatomic molecule, the molecular wave function can be symmetric or G, gerade, or antisymmetric or ungerade. So you can have these two possibilities, and the transitions, electric dipole transitions, because of the symmetry of the electric dipole operator, go from G to U only. You can have G to G transitions, but they cannot be electric dipole. And typically magnetic dipole transitions are suppressed by 50,000 alpha squared, basically more than 10 to the 4. So, but here we think maybe they're not as strongly suppressed. And indeed, we can actually see magnetic dipole transitions to these gerade levels. So you can see just not the best, but somewhat useful to look at trace. So the top transition, we know that it's magnetic dipole because when we use so-called pi polarization, or when our probe light polarization is parallel to the quantum axis, we actually see, rather than the central peak, we see the two side peaks, which is quite the opposite behavior what you'd see in an electric dipole transition. And then when we turn the polarization and we drive a sigma transition, instead the central peak becomes much more prominent. So it is a magnetic dipole transition that we can see. There have been predictions about the strengths of these forbidden magnetic dipole transitions in molecules. So for this M1, a prediction is such that the lifetime of these Gerade states could be roughly proportional to the length of the molecule. So again, the more weakly bound molecule, the easier it is to see these normally forbidden transitions. So we'd like to test this. And in order to check this, we really have to very carefully measure these lifetimes or line widths somehow, which is not so easy. We decided to just start by looking at the line width. So as I said, the electric dipole transitions, or Gerade to ungerade, they are about 20 kilohertz natural line width. These could be anywhere from 50,000 times narrower to who knows. So we have to be able to resolve very narrow lines. And of course, they're trapped in an optical lattice that gives the ground and excited states potentially slightly different Stark shifts. So what we do is we have to find so-called magic, either magic frequency or a magic angle for the lattice polarization. So here, luckily, it turns out that if we turn the polarization of the optical lattice, we can kind of almost cancel the lattice tensor shifts with the lattice scalar shift, and we get an overall Stark shift of just about 0 at the near 90 degrees here. So basically, we can make a magic wavelength lattice for particular pairs of these forbidden transitions, which is nice because then the lines won't be inhomogeneously broadened by the optical lattice. And so now these are the line widths, again, in the applied magnetic field. So we're looking at sort of the intrinsic line width at 0 field. So far, they're actually 1/20th of the electric dipole line width, which doesn't actually, this is kind of preliminary, and I think they might be much narrower than that. But it looks like they're definitely strong, not nearly as weak as we'd expect in a comparable atomic system. OK. And one more interesting piece of physics about these very weakly bound molecules is the possibility to look for quantum electrodynamics effects at a kind of high precision level. So again, I'm plotting this. I'm zooming in on this molecule recovery peak, really the one that's closest to the asymptote. And they're degenerate, so you can see one component of one and 5 components of the other transition. So we want to focus on the ones that are closest to the asymptote for the most greatly enhanced QED effects. In fact, the first order through QED retardation effect for this molecule is expected to exceed 10%, which is quite unusually large. Of course, always, so QED retardation effects are due to the fact that speed of light is finite, and the more you separate the two particles, the more sensitive you are to this effect. And of course, in all photoassociation experiments, the molecules are the atoms are quite far apart because these molecules are pretty big. But I think typically it's more like 10 to the minus, a part in 10 to the 3 rather than a part in 1 in 10. And then when they say they test QED in molecules, say in hydrogen too, it's a slightly different QED effect, but they're part in 10 to the 5, so much less sensitive. Moreover, it's estimated that even the higher, the next order QED effects are in part in 10 to the 2, which is also very large. In fact, our measurements already exceed 10 to the 2. So I think we can do kind of a nice job testing QED in this system. I think the bottleneck here is to improve the ab initio model just to have more fidelity in the comparisons of experiment with theory. So the goal for people who are trying to work on the model with us is to make sure it agrees, obviously, to spectroscopic precision with the deeper levels that we know, the levels that are not as sensitive to QED, so then we can have faith in the levels that are very sensitive to QED. And another interesting part of this is that We can measure the levels from the asymptote down to binding energy of 10 or even tens of gigahertz. So in terms of the length of the molecule, that the variation is from about 500 Bohr to less than 50 Bohr. So that spans more than an order of magnitude of the molecule size. So we can test this QED sort of contribution versus the size of the molecule. And there's some old work that's very commonly used, I think, to calculate QED for long range and sort of medium long. And there's a theoretical transition how to calculate it for one regime versus the other. But I don't think it's been experimentally observed that that's actually valid. But we're getting into the precision where this becomes really important. OK. So just a slide on the theory, although I'm not an expert necessarily in quantum chemistry, but our colleagues are working hard to improve the model so that we can extract as much possible information from the high precision experiments. So basically, this is they take what's called Hund's-Case A potentials for strontium-2, and they populate the diagonal entries of this Hamiltonian with those, and then you can see blocks. Here, these subblocks, they contain what's called adiabatic mixing of the two potentials. These are the 0 and the 1. And then these off-diagonal blocks include non-adiabatic mixing. So that's what we measured with the linear Zeeman shift, et cetera. And so when you solve this, at the end, come out hopefully very realistic potentials that actually agree with our data. And even though our data is very precise, this model does already agree to about 1% with the weakly bound levels. So it's quite good, but there's a little bit of room for improvement. OK. So as I promised a little bit at the end, I'll talk about a third type of experiment that we can do. Instead of one photon to probe the weakly bound molecules near the singlet triplet asymptote, we can use 2 photons to bring the molecule back to the ground electronic state. So basically, in this kind of experiment, we're probing a ground state dimer, and we call that a molecular clock. I guess it's just because it sounds cool, and also because we can really measure even narrower line widths and get a very high precision on various kind of fundamental physics properties. So if you think of a diatomic strontium-2 molecule in the ground state, you can think of it as 2 fairly massive, because strontium-88 is a heavy atom, 2 fairly massive balls in a spring. The spring constant is, of course, depends on the mass of the electron, because it's given by the electron-electron interactions predominantly. So this molecule is sensitive to 2 interesting effects. One is that these atoms are quite heavy, so they do gravitationally interact with each other. So in some sense, you might be sensitive to nanometer scale gravity effects between them. And in another sense, because the system depends both on the nucleon and electron mass, you'll be sensitive to any possible variations of the mass ratio of the electron to the proton with the same basic experimental system. So again, this is a schematic of such an experiment, just 2 photon with some common detuning from these levels. We can go to hopefully many different possible levels in the ground state. So we start off, of course, with weakly bound molecules, because that's where they're produced. But no reason why we can't, with one step, go to much more deeply bound dimers. So in fact, we have some experimental data that says, OK, we can do coherent transfer from the vibrational level in which they're produced to other vibrational levels. We can look at this. We can apply pi pulses and see Rabi oscillations. So it's a coherent transfer. This is a picture in time. Again, looking at losses of molecules or gains on the gray trace, either way. Picture in time. This is a picture in frequency domain. When we scan the frequency, we can see this resonant loss. The peaks we see are transform limited, which means the width are basically limited by the length of the pi pulse we apply, which is where we want to be. We can try to reduce that transform limited line width by applying longer and longer pulses. And And then we, of course, run into limitations of the overall coherence because at some point we just don't get any signal. So far, the narrowest we saw were about 100 hertz lines corresponding to 20 millisecond pulse lengths. So ideally, we would like to narrow this by another order magnitude or 2 orders of magnitude down to hertz level. The reason it's now limited to 100 hertz, I think it's because of the differential lattice Stark shift. They're sitting in an optical lattice which is at 914 nanometers, which happens to be a magic wavelength for the atomic transition. But so here, when we go from one molecular vibrational state to another, although the polarizabilities are quite similar, they're just not the same for a weakly bound molecule versus deeply bound molecule. So we just get differential lattice Stark shifts. And we measured them, and they're about 4 hertz per milliwatt, and exactly kind of the same, roughly, that would give this line width. So we just need to do something to flatten this out, either by finding the right kind of sweet spot in frequency or in polarization. And I think it should be possible, but that requires a bit more experimenting. So basically, that's really not the right color scheme, but that doesn't matter. These are all Frank-Condon, or actually all transition dipole moments from all the ground state levels in our molecule to all the excited state within that manifold. And everything I've shown so far has been confined to this little rectangle because we were working with weakly bound molecules. But luckily, a lot of the strengths, they recur, a lot of the strong transitions, they recur all the way to very deeply bound molecules. So with exactly the same method that I showed in the previous slide where we saw Rabi oscillations, there's no reason why we can't see them. We just need a different wavelength, which we almost have now. So we can indeed, hopefully, without changing the experiment much, make very deeply bound dimers. The only trick here is because then for the 2 photon, the 2 wavelengths will be quite different, but they can be connected with a frequency comb that we also have, and so it's not actually a problem. Now, just briefly, I'll show a bit on why. So when I say this might be useful for constraining new interactions at the nanometer scale, what I actually mean. So this plot is stolen from this paper here that shows constraints on this form of non-Newtonian force, this Yukawa type potential that several theories predict that might be modifying gravitational force. Versus the log of the length scale. So this is a micron, this is a nanometer. And you can see the constraint, when you get down to a nanometer and these van der Waals force region, the constraint is actually quite poor, is 10 to the 27. So we really don't know much about that region, to say the least. And here, if you have an isolated diatomic molecule that's theoretically fairly simple to describe in terms of its electromagnetic interactions, then you do have basically a pair of fairly heavy atoms that are separated by something like 0.1 to 3 nanometers that do interact gravitationally. So if you can really understand the other contributions to their interactions, you can at least maybe do a better job than this constraining it. So I showed a few molecules, the ytterbium-2, strontium-2, and hydrogen-2, how they could potentially contribute to this very poorly known region. And hydrogen, of course, is a very tightly bound molecule, so it's great, but it's better actually at even tighter distances. But in terms of this nanometer to 0.1 nanometer, these alkaline earth type dimers, I think are very promising, especially strontium, because it's a little bit easier to both model and measure than ytterbium. And actually, if you look here, so without even taking any data, any new data, just the very limited amount of data that we already have already looks like we're sitting pretty well here, right near the existing limit. This just shows a little bit better. So this shows the constraint that from some simple modeling, and this just from slightly fancier modeling, shows that actually these are quite pessimistic, and in reality, I think they'll be a little flatter. But anyway, this is just based mostly on data from 2 isotopes from our lab and from another lab in Innsbruck. one needs at least 2 isotopes because these are mass-dependent interactions. But these are mostly quite weakly bound levels, and we gain exponentially by going to deeper dimers. So that's the goal. And another hope is that, clearly any gravitational interaction will be completely swamped by other interactions that are electromagnetic in nature. But instead of doing 2 isotopes, if one adds a 3rd isotope, then one can try to resolve some of these other mass-dependent effects that come into play. So the more isotopes you have, the more handle you have on these effects. So in theory, one would start with a Born-Oppenheimer approximation and then add a mass-scaled Born-Oppenheimer approximation that sort of works for all isotopes. And then one would add mass-dependent corrections that could be resolved by studying different isotopes. So that's one thing. And the other thing one can do with these deeply bound molecules is just run a molecular clock. So for the previous experiment, the idea is to measure fairly precisely a whole bunch of levels, including very deep ones, for that constraint. For this experiment, one would focus just on 1 or 2 transitions, but do it extremely well. So here, I show, for example, if one measures a transition from the 0th vibrational level to one in the middle here, and one from here to one of the weakly bound ones, and take this ratio of the 2 frequencies, that ratio ends up being quite sensitive to any drifts in the electron to proton mass ratio, but completely insensitive to any intermediate clock you use to measure these frequencies, because that happens to cancel out. So it's a kind of a nice thing. Here again is the sensitivity of the vibrational levels. So these binding energies, this is at the bottom of the potential, this is at the top of the potential. So these are sensitivities of the binding energies to the fundamental constant, mass ratio, and alpha. So you can see the sensitivity is very, very high for this middle level and quite low for these anchor levels on the top and the bottom. That's why we go from the middle to one of the anchor levels. And also you can see that the sensitivity of the mass ratio is much greater to that of alpha, at least by a factor of 4. Basically, it's a pretty clean system. And overall, the sensitivity to change in the mass ratio is given by this ratio. One is, so in the denominator is this sensitivity, which this logarithmic derivative, which is actually nothing special here. There's no special enhancement factor or anything, so that's on the order unity. But where we can win in this system is an extremely high precision here in the optical lattice. So if we manage to get something like a millihertz, it will be 3 parts in 10 to the 16 on the mass ratio. Now, to compare it with something that's already in existence, a comparable lab-based molecular clock that's published constrains the mass ratio variation to about 6 parts in 10 to the 14. So I think a lattice-based system could be significantly more accurate. Now, there's a very recent experiment also with a methanol rotational mode. This is an astronomical experiment that seems to constrain the variation to a part in 10 to the 17 per year. Now, this is kind of hard to beat in the lab because we don't have the lever arm of 9 billion years. We only could do it for a year or 2. But again, astronomical measurements and lab-based measurements are kind of complementary, I think. So I think it's still important, even if we don't quite get to part in 10 to the 17. Okay, so just to summarize, I'll just summarize again what I discussed. We have used all optical technique to make ultra-cold strontium dimers in an optical lattice. And then we did some high-resolution precision measurements on on the weakly bound molecules near the singlet S triplet P atomic threshold. We observed some unusual, kind of unexpected asymptotic and non-adiabatic effects through the Zeeman shifts, particularly quadratic and linear. And we observed some forbidden transitions that should have been even more forbidden, but they're not because of this asymptotic physics. Now we are working on getting some a better leverage on the QED contributions and the Born-Oppenheimer approximation for the molecular clock and constraints on potential nanometer scale mass-dependent interactions. Thank you.
this non-adiabatic, with a large magnetic susceptibility, you get something very similar in a diatomic polar molecule, where the polarizability also diverges as the rotational constant goes to 0. And there it's associated with the existence of a permanent electric dipole moment in the body frame. So I'm wondering if that's the explanation for the magnetic, the divergence of the magnetic susceptibility. In the body frame, there is a permanent magnetic moment.
You mean the
Or orbital moment.
you mean the electric dipole polarizability grows as you go to more weakly bound molecules?
Just for the same reason, because you have a
Right.
fixed dipole moment on top, and as the rotational
Right.
constant goes to 0, you just get a divergence.
I would think
So
it
going
would
from
be
a 1
related.
over a pure
Yes.
dipole to a highly from a highly polarized one to a fixed dipole.
Right. I would think they're related. But again, you're talking about highly rotationally excited or highly vibrationally excited molecule,
Well,
or
just taking the rotational constant
yeah.
down gives you the same
Okay.
picture.
Any other questions?
No. I'm just following up on what Charles was saying, because I'm not sure I'm really understanding. The idea there is that, if I've understood correctly, you've got a body-fixed electric dipole moment in a system that cannot have an electric dipole moment in any eigenstate of rotation or vibration. And then when you reduce the space in between the rotational states, then it's easy to create electric dipole moments in those superposition states. It doesn't really diverge. It couldn't get any bigger than the body-fixed one, right?
Well, but it's a susceptibility, you see, so the polarizability does diverge.
Okay.
I mean, actually, if you take the classical limit, you have a fixed thing, and so it has a permanent dipole.
But here, you've got fixed magnetic moments that exist
Right.
already in the eigenstates, right?
Right. Sure.
So, is that
right.
gonna really be the same thing?
Well,
Ask the speaker.
I mean, I'm not sure. I guess if you have a polar molecule and then you make it, you excite it vibrationally to more and more loose, and the molecule becomes looser and looser, I think the polarizability, the electric dipole polarizability actually falls. It's not, so as you make the polar molecule more and more loosely bound, it does start acting more like a pair of atoms in that sense.
That's
it's,
right.
it's not very, right. But here, this magnetic susceptibility seems to, as you make it looser, it actually grows hugely. So qualitatively, there's something very different here.
Any other questions? That wasn't really a question.
That's right, that wasn't really a question. It was just a follow-up.
Right.
Okay, so let's come back to the molecular clock and the mass ratio thing.
Okay.
Now, I probably misunderstood this, but it seems like, well, you're hoping to get to millihertz in those.
Optimistically, yes.
But now, is that on the same kind of transition that you were struggling to get 100 hertz on, or is this something different?
Yes, it's the same. But I wouldn't say we were struggling yet because we know why it's 100 hertz, and we just
5 orders of magnitude goes. What are you going to do to get 5 orders of magnitude?
Yeah, so we can get, I think we can get 2 orders of magnitude by removing the lattice shift. And then, we don't need to get a millihertz because one trace takes, 30 seconds. We don't need that. We don't need to measure it in 30 seconds, although that would be ideal. We can take a few days to measure it, so some averaging down would have to be involved. I think, so yeah, the main thing is, I think if we can get 2 orders of magnitude on the line width, that would be great already. And then the main thing will be controlling systematics. I think that's more of a difficulty than narrowing that line width.
So what you're hoping to do is get to a hertz and then split the line to.
Split the line, and splitting the line again is maybe okay, but some systematics are a bit challenging in this system.
So it seems like one of the big challenges there is that if you've got inhomogeneous broadening, which presumably, from what I gather, you're not going to be able to drive to 0.
Inhomogeneous.
Due to the lattice light shift, is what I mean.
Well, we might on the hertz level. We might. It depends. We might have to choose the level pair wisely, but I'm hoping that we would be able to go to the hertz level.
Yeah, to the hertz level. But what I'm worried about is if that's at the hertz level due to inhomogeneous broadening, then you're going to try to knock that down to the millihertz level. And inhomogeneous broadening is sort of notorious for making it difficult to split the line.
Right. Yeah, you're right. I mean, in some like preliminary estimates, we thought we could do that millihertz. I think it would probably mean that the inhomogeneous line width would actually be much better than a hertz, and that we would just maybe transform like pulse length broaden it to a hertz or 10 hertz or something like that. So you're correct. Yeah.
What I was wondering was, do you have any ideas that maybe you could go to transitions where everything's in the ground state of the lattice, so you can get rid of that issue?
We are. I mean, I think we're 95% in the ground state of the lattice.
Already?
Yeah, we're very cold, and we're very cold, but it's just really that the weakly the excited vibrational levels do have a different polarizability at that wavelength. So, I mean, one has to use tricks in order to avoid that inhomogeneous broadening. It's just the tightly bound molecule sees a slightly different Stark shift than the weakly bound molecule. And then as you sample, the lattice, different areas of the lattice, you get that inhomogeneous broadening.
Well, maybe I didn't make myself clear. I'm thinking whether the molecule is sitting in the ground vibrational state with respect to its own center of mass motion in a lattice site.
Uh-huh.
As opposed to its own vibrational state. So I'm
Right.
thinking, if you...
Like Lamb-Dickey type?
Yeah, exactly. That's right. But I mean, I don't think the issue is so much whether it's Lamb-Dickey, it's whether it's predominantly in the ground. So I guess perhaps the right language would be, is it in the ground band of the
Right.
of the lattice? And when you make a transition, can you make a transition to the excited, that is vibrationally excited molecule being in the ground band?
Yeah.
It's vibrationally excited, and then you shouldn't have
But that's what we do, and I think you do have inhomogeneous broadening because ultimately, when you probe a transition, you have quantum superpositions of the two levels, and if the two levels experience different Stark shifts, that just ruins the coherence of your quantum superposition. So even if you're perfectly in the ground band of the lattice, you just have the superposition becomes shorter lived because the two components of the superposition experience different Stark shifts. Not only different, but as you sample, the center of the lattice beam versus the edge of the lattice beam, you get that problem. Yeah.
Any other questions? Okay, a few announcements. So Tanya has a train this afternoon, so there will be no tea with the speaker this afternoon. However, we do have a special JQI seminar. Na-Young Kim from Stanford is going to be talking about exciton, polariton, quantum fluids, and that's at 4 p.m. in the CSS conference. So why don't we thank